Hello guys. So now what I will discuss is something really beautiful. We will use R coding for that. Okay. So let's revise the simple linear regression a bit. So what is there in simple linear regression, guys? We have, just ignore my bad handwriting. So we have that yi, which is following beta naught plus beta 1 xi plus epsilon I, and epsilon I follows something, say some distribution. So let's assume normal 0 comma sigma square. So what we have got till now, we have minimized, and we have got minimize the loss function. Let's not go into that. What we need is that we got this corresponding estimate, beta naught hat plus beta 1 hat xi, right? We have sort of got this yi hat. We also got that yi is actually called, it's actually divided into these two stuff. Okay, this is called the residual stuff. So there are two important questions. What is the difference between residuals and epsilons? So difference epsilon versus residuals, this question. Another question means that what is the difference between beta naught hat versus beta 1 hat, beta naught versus beta naught hat, and beta 1 versus beta naught, beta 1 hat, okay? These are two questions that are really like beautiful, okay? I love these questions because it makes me makes my understanding much more concrete, okay? And also another thing that is really interesting from my end is that the variance of the expectation is the bias is 0, but the variance of this beta i's is proportional to sigma square. That means the more is the variance, the more is the uncertainty of, more is the bad behavior of beta naught hat. Like the more beta naught hat can and beta 1 hat can actually approximate the less better, actually, you understand. So suppose beta naught is like this and beta naught hat is like this. So more the sigma square becomes more and more diluted in some sense. So beta naught hat being more closer to beta naught is actually being diluted every single time the sigma square is increased. So these four things we will actually show by experiment in R coding, okay, by doing simulation. So let's go to R coding now. I hope all of you can see the screen now. So what I will do, I will first like take some random xi's. So I am just taking an x sequence of xi's from 0 to 1. If you see 0 to 1 with 0.01 interval, okay. And then I will do y. I will just simulate y. Okay, remember yi is following xi beta naught plus beta 1 xi plus epsilon I. So what we are doing, it's beta naught is equal to 2, beta 1 equal to 5, and xi, the corresponding xi's are fixed, you know that. And this is the epsilon part, I part, okay. This is the epsilon I part. I can write it as epsilon. So let's write it as epsilon as normal. Observe that we are selecting the length, the number of x's is there. We are selecting that many epsilon i's, and we are selecting normal 0, 1, okay. And we are correspondingly adding epsilon to this x. Let's simulate epsilon I. Oops, I have done it. This spelled it wrong. Okay, let's try to see what does epsilon look like. It looks like this, right? So it's like a sequence of epsilon normals. Let's not go into how it looks like, whether it's normal or not. It's obviously be normal, similar for normal. Now let's define y. Y is defined as this. So observe that beta naught here, beta naught is equal to 2, and beta 1 is equal to 5. Let's write it in that manner. Beta naught plus beta 1 times x. Okay, let's save this in these variables and let's try to simulate this one. So it's y is equal to beta naught plus beta 1 x plus epsilon, which is what we want. So y is like this. Okay, so we have got xi's and yi's. So we have know the actual beta naught and actual beta 1, which you actually don't know in many of the statistical problems, right? It is just for experimental purposes. Now let's try to understand and see plot of xy. We just plotted xy looks like this on the right hand side. Okay. So now I just let me play around with this whole. So if we just make it the variance smaller, so this is the variance. Okay. So we are changing this is the variance part. If we change it, let's try to do it again from scratch. Also, it becomes much more less. So the variance of the epsilon I is therefore reducing it. The variance is reducing. So therefore it looks like this, right? So now let's fit a linear model to the one, okay? Where the variance is one. Let's try to run it. Yes. Now let's do the linear model. So linear model is done by this lem function, and we have done the linear model, fix the model. It's like estimates are fixed. Okay, let's first see how it's fixed. So first we do is plot xy, and then we add this AB line, which adds to the plot. Okay, and it's the best estimating line looks like this. That's really cool. Now let's try to see what is exactly beta naught hat and beta 1 hat. Oops, what is the problem? Summary of linear. Oh, wow. There's space. I've given a space. Yes. Now observe this very carefully. Let me zoom out a bit. Zoom in a bit, I mean. So observe this, that the beta naught, what was the beta naught? Beta naught was 2, right? And here, what was the beta naught hat? Estimate is the intercept is the beta naught hat. It's 1.9. Now what is x? The x intercept, that is a beta 1 hat, that is 5.2, okay? It's 5.2. And the multiple R square is 0.7. Okay, it's quite a good fit. Multiple R square is actually the square of the correlation that you have seen. So you have understood that this beta naught and beta 1 hat are actually different from beta naught and beta 1. Okay. So let's do another experiment. Let's do this again. Okay. And you will see that the beta naught will be changing. So beta naught is actually a random variable, not hats. Sorry. The hats is actually a random variable, but not hats. Let's fix the linear model again. And let's see the summary. Oops, again, that mistake. So if you observe this, like the y's are changing every time and the x beta naught has also changing every time. See, it was 5.2, it reduced to 4.8. So every time you similar different random variable, the beta naught hats are same. But essentially we are doing from the same basic equation. The fx is same, but the epsilon i's are different. Okay. Now what are residuals? So we understood the difference between beta naught hat and beta 1 hat, and the beta naughts and beta 1. So that is the difference between estimates and the parameters. Now what is the residuals? The residuals is what? Let's see the summary again. I will change it here. One. If you observe the residuals, actually the residuals is like this. So median, the mean of the residuals sort of 0.11, and the residual summation will be 0. We know that from the normal equation, but the median is this. Okay, the minimum is this, the maximum is this. Sort of, you understand that this is different from something, right? So what is EI? EI is actually the residuals. Let's save it. Residuals, let's save it here. Residuals is actually what? It's actually like YI, okay? The predicted parts. I think I have written a thing over here, yes. Let's see this. So let's predict this. So it's actually y minus predict, or you can write it as y minus, yeah, predict of linear model, comma, the x. Okay, so this is a yi hat part. So if you just do it, it's a yi hat part, and the correspondingly, the beautiful aspect is this, that this is the residuals. Let's try to see it. There's some errors. What error did I do? Yeah, it will be list. X is equal to x. Will it do now? So let's see the residuals. Looks like this. So let's now plot the residuals and the actual epsilons. Observe that they're almost equal, but they're on a linear line, but they're almost equal, but they're not the same, okay? That's an idea. So that's the beautiful idea of the residuals and epsilon. They are almost same, but they are not equal. So that's sort of an estimate of that. Okay. So therefore, understood difference between residuals and epsilons. Now, the variance. So suppose let's do this again. So let's increase this to 5. Okay, let's plot this and change the sigma square to 5. It looks like this. Almost looks bad. Let's do it to 2. Okay, then it will make much more sense. Okay. Oh, so let's do it for 0.1 ones and 0.1 ones. Okay. So for 0.1, it looks like this, and let's see the residuals, linear plot, and AB line, and residuals. Not the residual summary. It's like 0. The beta naught is 0, so it's at 1.9, and it's 5.04. Okay. You got this point, 1.96 and 5.04. Let's do it for 1 now. We do it for 1, you will get that it's 1.96, it's 2.18, and it's 4.85. So it's like a lot of differences there. Okay, the standard error difference is there. Essentially the idea is that it's like varying. Okay, it's varying in that sense, varying from the corresponding actual beta naught much more when the sigma square is increasing. Let's increase to 5, and you will see it's like the difference now. Although it's minus 0.2 and 9.6, which is nowhere close to 2 and 5. Okay, so essentially this is the basic idea, that it's actually changing much with this proportional to sigma square. So therefore the variance is proportional to sigma square. You also understand from the standard deviation also, the calculation of the standard deviation also. So the motive of this session, last session of the series, is that we have understood how variance of the errors become large and how the estimates change. It varies much more from the center. It is actual, it's because the bias is 0, the actual value. And we have also seen the difference in residuals and epsilon. They're almost close for estimates of one another, and the difference between the estimates and the parameters. So therefore, we end this linear regression, simple linear regression, small course out here. We'll see in the next series and the next video. Stay tuned and stay blessed. And don't forget to subscribe, comment, and share to your peers, and learn together and enjoy together. Bye-bye, and always love sharing knowledge. Bye-bye, and see you in the next video.